लिंक तो हाँ लिंक तो आपको भेजा चुका है सब।
చెప్పరా ఇంట్లో లేదా?
Hello, can you hear me?
ఎంత కావాలరా?
This is Anil Kumar. I can't see anything.
ఎవరా?
Yes, sir, we can hear you. Good morning, sir.
Good morning, but I don't see any screen which shows me what's going on here, there.
ఒక గంట ఉంటే ఏమైనా చూడగలము. ఎక్కడ కష్టం ఏంటి మళ్ళీ టైల్స్ చదవలేదు లేకపోతే అంటే లేకపోతే ఒక గంట బయలుదేరుతా.
Very good morning, professor. People are getting ready, है ना? Actually, I come around 8:30 to the institute. उसके बाद मैं फिर निकल जाता हूँ. Maybe around 10:30 again I go back.
लाइट जरा ज्यादा आ रही है, ये आगे वाली ऑफ कर दो. बात तो जाएगी ना पूरी? हाँ सर, ठीक है.
Initially asked them to increase this number, but they have not done it.
वीडियो ओपन करने में बोला. हेलो, आवाज आ रही है? बुलाओ उसको. Good morning to everybody.
Good morning, sir.
Is I am audible to everybody?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
May I request to open your video, please? So very good morning to all of you present here. Honorable Director, Sir, Professor Anand Shauji, distinguished faculty members, distinguished speakers, and my dear participants. It is a matter of great pleasure and pride to us that IITM Gwalior is going to conduct 4th ATAL FDP program in this series, in this session, and that is on quantum computing. So I'd just like to welcome everybody who are present here through online mode from on behalf of ABV IITM Gwalior. Very good morning once again to all of you. So just I'm giving some introduction about this FDP. Our institute, that is Indian Institute of Information Technology Management in Gwalior, Madhya Pradesh, is an institute of national importance set by Government of India in 1997. It is an effort by Ministry of Education towards creating professionals in areas of management and information technology from the same institute. This institute was created for facilitating higher education, research and consultancy in areas of information technology and business management. Initially started as IITM, this institute was prefixed with ABV in 2002 to honor the then Prime Minister Atal Bihari Vajpayee. So far as departmental concern, this discipline of applied sciences was established in 2006 to impart the fundamental concept of science to undergraduate and postgraduate students. The department is equipped with computational and nanoscience technology lab with high-speed computing facilities. It has an international national research reputation with several research contacts and collaborations across the globe. Currently, the department is running projects sponsored from DST, DRO, and so many other funding agencies. It has conducted so many faculty development programs sponsored by MHRD, AICT, and institute itself. So the objective of this program, that is quantum computing, you know, that is a thrust area and big growing challenge for both science and technology. Quantum computing is without doubt one of the recent topics at the current frontiers of computing or even of the whole science. It sounds very attractive and looks very promising. There are several natural basic questions to ask before we start to explore the concepts and principles as well as the mystery and potentials of quantum computing as well as quantum computers. This faculty development program on computing aims to understand the elementary concepts of this emerging area for the faculties, research scholars of institutes, colleges, labs, and other academic institutions. And it is anticipated that in next 15 years, you will have your quantum computer in your hands everywhere. So the contents of this FDP to be covered this time in this 5 days, that is about fundamentals of quantum computation, quantum mechanics of versus quantum computing, quantum information processing by NMR, physics of quantum computers, quantum entanglement, quantum gates and circuits, quantum algorithms, teleportation and superdense coding, quantum noise and error corrections, NMR quantum computing, topological and computing, programming on IBM composer, that is Qiskit, lab hands-on lab practice, and quantum computer physical relations. So this will cover all of the elementary understanding about quantum computer and computings to our young faculties and research scholars who have a wide future in this area. So with this, I am Professor Pankaj Srivastava, coordinator of this program. And now I request our director, Professor Rajan Sahu, to inaugurate this session and with his inspiring words. So Professor Rajan Sahu, please.
Thank you, Professor Pankaj. Very good morning to everybody. I think.
Good morning, sir.
Very good morning.
Good morning, sir.
The research persons, the participants, faculty, and everybody present, off and online, because today online has become the order of the day, because as the physical distances has to be maintained and the gatherings has to be limited, the online mode has taken up over the offline mode in large cases. So this has given an impetus to the digital strategy or doing things digitally. It has many advantages. The advantages are it is clean, cost effective, wider reach, and you can have more of research persons from anywhere of the globe. So if we analyze, the computers have become the order of the day. Everywhere now we have computers. So the Industrial Revolution 4.0 takes on this, and we are seeing massive changes everywhere, whether it is service sector or in the manufacturing sector. So as computers are becoming inherent part of all business processes and activities, the processing power of the computers need to be enhanced. And we understand the Moore's law that the processing power gets doubled and price gets halved. But there is limit to everything. Now the big data, the AI that is getting into the chips, in-memory processing, real-time data analysis has become the order. In such cases, the only way that you have to do it is to do it fast. So in doing so, we have increased the processing power. But there is a limit to it. The limit is how many transistors we can put into the chip. Because as we put in more numbers, these are low power circuits. Now, if we put in more chips, more transistors, then the heat generated by them will be more than the heat that is required to operate them. So gradually, they will not be able to sustain it. Hence, we have to look forward for ways of doing it with a lesser time. A better technology is what we call today is the quantum computing. In normal circuits or in transistors, we have two states, 0 and 1. Either you have power in them or you do not have power in them. But if these states can be increased, then we can have more of processing from an individual transistor itself. So the quantum computing is a step in that direction. So what usually takes years in computing by the traditional computers, or what we call as today supercomputers, can be done in minutes. Can be done in minutes. Because we have, in evaluating a system, a computer system, what we say, these are information delay reduction systems. We try to evaluate a system by saying how much time it takes to process. Now, if that is a single parameter, how much time it takes to process, so the traditional computers and their enhanced version of the servers and the supercomputers are reaching their limits. So the only way, as I said, is that you have to increase the number of states. So if we increase the number of states, then automatically the same transistor will be now more productive. And it would take almost 1,000 to million times faster, as it has been said, than the traditional computer. So I am seeing here a host of topics within this institute. When we were beginning to have quantum computing in the early part of this century or the later part of the last century, when we started, it was looking as a concept, something that is theoretical, will take time to reach. But today, as it is visible that large companies are investing a host of their investments into the quantum computing. So suddenly it will become the order of the day, and we need to keep updating ourselves, and to be a leader in this, we have to move fast. So I wish this conference all success. And I also thank the AICT, which has taken this step in promoting such conferences to a wider reach. And thanks to all the research persons, thanks to all participants, and thanks particularly to Professor Pankaj Srivastava, who has taken this initiative. In doing a conference, a lot of background work takes place. So I thank each and everybody who have been associated with this conference. Thank you, everybody.
Thank you, sir. Thank you. Thank you very much for your inciting words for this faculty development program sponsored by AICT. So without taking much of time, I would like to start first inaugural lecture by Professor Arun Kumar Pati, who is present here. Professor Arun Kumar Pati. Yes, is I am audible, sir? Professor Arun Kumar Pati. को बीच में हाईलाइट करो, पिन करो, पिन. Professor Arun Prati, sir.
नंबर है तो कौन सी बात?
हैं? Sir, mic on. इस पर आने रहे क्या इसमें?
लाइन में ये हालत है कि कभी कम्युनिकेशन सही ढंग से रीच नहीं करता।
उनको पिन करो, पिन कहाँ पे है? ये यार अभी था तो ये के बाद अरुण पति था ना वो। हाँ ये है ना, ये इनको करो। हाँ हाँ सॉरी। Is I am audible, Professor Patil sir? Please open your mic, sir. Sir, is I am audible? हैं?
कर रहे होंगे ना, कोशिश कर रहे होंगे तो इधर उधर हो गया हो।
There is some आवाज आ रही होगी. There is some network problem from the Professor A.K. Pati. So please wait for a while. He is trying to link with us. हुए क्या ऐड हुए? हैं? तो ढूंढ लेंगे. ऐड नहीं हुए? हाँ? अरुण कुमार नाम है। जी शंकर जी। बोलिए बोलिए बोलिए। अरुण पति होगा। कॉल लग जाता है। कॉल भी नहीं लग रही है। हेलो। क्या करें? लगेगा काम करता हूँ।
You can give them a break. The break is the participants go. We are tell them that we are getting in touch with the professor. Can आप शुरू करो?
क्या?
10 बजे शुरू करो।
मैं दे दूँ क्या? या तो अभी You unmuted? Unmuted. Okay. So, dear participants and my distinguished, आगे तो करो. बंद करो. Yes, Professor A.K. Patiji, sir. Is it audible to you?
Yeah, I was trying to log in since last 40 minutes. There was a problem with one of my laptops, so I now using another.
Okay.
Now I can join. Yeah, I can
Okay,
hear.
okay. Thank you, sir. So, printer kar diya? Okay, sir. Now, dear participants, now Professor A.K. Pati is on our screen and is ready to give his inaugural lecture. So, just I would like to introduce Professor Arun Kumar Pati. Professor Arun Kumar Pati is a professor in Quantum Information and Computation Group at Harishchand Research Institute, Allahabad. And before joining here, he was a scientist at Theoretical Physics Division, BRC, Bombay. During his tenure at BRC, he was a visiting scientist at University of Wales, Bangor, UK. Then he was an invitation to Institute of Physics, Bhubaneswar, India. He has visited and delivered talks at many universities and institutes, including University of Bristol, UK, MSRI, Berkeley, University of California, MIT, Boston, USA, Bell Lab, NJ, USA, Naval Research Lab, Washington, DC, NASA, University of South Carolina, University of New Mexico, Perimeter Institute, Waterloo, Canada, and many more. His research areas include all aspects of quantum information and quantum computation, the theory of geometric physics and its applications. Among his important discoveries are the no deletion theorem, geometric phases for mixed state, remote state preparation protocol, the no hiding theorem, and stronger uncertainty relations in quantum mechanics. The no deleting theorem can be found in Wikipedia. He has more than 150 research papers in international journals and conferences on these topics. To his credit, he has edited 2 books. First is Quantum Information with Continuous Variables, Quantum Aspects of Life. His research papers have been highlighted in Nature, Nature Asia, Science, and many national and international newspapers. He is recipient of many awards. Some few of them, just I would like to quote. He is honored with KP Chair Professor at Jiangnan University, China, CBOS National Fellowship from Department of Science and Technology in 2019, World Rank in top 2% scientists listed by the Stanford University, USA, and Distinguished Alumni Award from the Minister, Berhampur, Odisha. So there is no need to go for so much introduction about Professor A.K. Pati. He is a distinguished and very renowned professor and scientist and research expert in quantum information and computation group. So I request Professor A.K. Pati to continue his lecture, inaugural lecture, to our participants. Thank you, sir.
Thank you, Professor Srivastava, so for this nice introduction. So I was trying to log in for last 30-40 minutes, but there was some issue with the sound, so I am okay now. So let me start sharing my screen. Can you see my screen now? Are you able to see?
On right.
Let me try to make it full screen. Sometimes it works, sometimes it doesn't work. So it is okay. So okay, so are you able to see my slide?
Yeah. It's okay, sir.
Okay. So I'm going to tell a flavor of this subject that has been developed over last more than 30 years, and over last 5 to 10 years, there has been a lot of interest not only from academic people but also from government and from private company and industry side and so on. So many people would like to know what is really this field of quantum computing and quantum technology is all about. So I will try to give a brief flavor of the subject. So here is this title, Quantum Computing and Quantum Information Technology. And I am at HRI Allahabad. So if you want to look at our group homepage, you can visit in this site. Okay, so the plan of my today's talk is I will try to tell you something about quantum computing, quantum communication, and quantum information technology. What is the big picture here, and then future of this quantum information. Okay, so when you think of information in classical world that all of we are familiar, essentially we store information in classical bits like 0 or 1, and that is kind of basic unit of information that we all familiar. And present day computers and in fact all other information processing devices that you are using, they store information on transistors switching between on and off state. So two distinct states like on and off, they may refer to 0 or 1, and that represents two possible states of a classical bit. And then what you do, you perform various tasks according to classical laws of physics. When I say classical laws of physics, what I mean that you can use either Newton's law or maybe you can use Maxwell's equation and so on. So what is strange about, what is crucial thing that you notice here is in classical world, you never find the logical state both at the same time. That is, given a classical bit, you will find only in 0 or 1. When you think of computation, essentially this is a device which takes a string of bits and produces a string of bits, classical bits. So roughly it is like a device which takes input and processes the information and gives you some output. So this is all about whether you talk about desktop or laptop or even any high-end computing device. Essentially, this is what's going on. When you think of communication, you can imagine two persons like sender and receiver, and sender can encode some information and send that to some channel, communication channel, and that could be, telephone or video or maybe face-to-face or could be email, anything you can think of that we are using currently. And receiver can receive the information and decode it, and also he or she can send it back to the other person, and this process can go on. And there can be also noise acting on this channel, and you have to take care of your communication channel, what happens when it acts upon some noise. And this physics and communication and computation, before 1980 or so, it was thought that there are two different subjects. But slowly to realize that physics and computation, they are not really different, they are intimately connected. Why it is so? Because if you think of the computation, it is essentially a physical phenomenon happening inside a physical system. And this insight, it may sound simple, but it was a great insight due to Ralph Landauer, who realized that ultimately information is physical. And this view leads to physics of computation. And this also gave a motivating factor to realize so-called reversible logic gates by Charlie Bennett in late 80s, which actually paved the way towards quantum computing. So physics is deeply involved in fundamental work, which ultimately leads to various technological developments. Nobody can deny that. And you can cite many examples starting from computers to internet to electronic devices to communication systems, and recently this emerging technology, what we are all familiar about this quantum technology. So if you ask the question, how did this field start? So it started around 1985 by David Deuss, but a little before that, in 1982, Richard Feynman, who we all know, one of the greatest physicists of last century. So he was trying to ask the question that what will happen if you try to simulate complex quantum systems on a classical computer? Can you do it, or will it be very inefficient, or what will happen? So that question finally led to this question that what can happen if you store information in two distinct states of a quantum object? But he did not pursue this line of thought further. But it was great initiative by, or great, revolutionary idea by David Deuce, who realized that not only you can do that, that means you can store information into distinct set of a quantum system, but also you can what do is you can exploit so-called this quantum mechanical superposition, and that allows you to do a new way of storing information, and also you can process information using these kind of quantum states. And essentially, your quantum computers are nothing but devices that can perform computation using principles of quantum theory, which is the ultimate theory of nature. And as you can see, the idea of quantum computer was originally due to David Deuce in 1985. And for this groundbreaking contribution, he actually also received Fellow of Royal Society in 2008. And there was another motivation, but this is not the prime motivation, that was called Moore's law, which tells you it is not a law that one can prove or can derive, but it is kind of empirical observation, which tried to state like this, that the number of transistors on a chip doubles every 24 months. And this has been a guiding principle for high-tech industry since it was coined by Intel co-founder Gordon Moore in 1965. A decade ago, companies were building chips at 500 nanometer level, and currently IBM tried to produce about 7 nanometer, and in the future they may produce even at smaller scale. And if you look at the trend, how the number of transistors grow with year, you can see that by 2020 or 30, you will reach transistor size which is about 2 nanometer across the length size. That is about 4 atomic distance. So all we know that once you reach that scale, classical physics will not be able to you will not be able to apply classical physics. So it means you have to somehow bring quantum mechanics to understand what is going on at that scale. So when you think of a quantum computer, the essential, the fundamental unit of quantum computer, or quantum bit, this quantum bit is a new notion that was introduced by, as I said, by David Deuce, but this name was given by Benjamin Schumacher, who is also one of the founder of this field. So essentially, a quantum bit is the following: that, so as I said, you can think of a classical bit like 0 or 1. But once you store information in quantum bit, you can also store in 0 or 1. That is, you identify two distinct quantum states like spin up, spin down. So if it is spin up, you say it is 0. Spin down, you say it is 1. But then we know that because of linear superposition, we know that electron can also remain in spin up and spin down state. That is a linear combination of up and down. That, if you translate to logical state, it means you can have a state which is like 0, something 0 plus something 1. Okay, that means your new object, which we call quantum bit, that can remain both in 0 and 1. So you can think of a quantum bit. You can actually realize quantum bit from any physical system, starting from electron spin to photon polarization, even atomic levels, and so on. So what you realize now is thus there is some kind of inherent parallelism which is coming into play, and that is responsible for this new type of computation, what we call as quantum computation. Why I say this inherent parallelism? Because your quantum state or your new logical state is able to assess simultaneously both 0 and 1, unlike your classical bit, which can only be found in 0 or 1. At a given time, it is only in one of these logical states, that is 0 or 1. But this quantum bit can have access to both 0 and 1. So that is the kind of parallelism you realize when you go to quantum computing. There are more differences which I will try to highlight. I will not go in detail, but I will try to highlight those fundamental differences between classical information and quantum information, which helps you to understand more deeply what is really going on. Okay, so here is a pictorial way to look at this quantum bit. So as I said, you identify two distinct states like up and down, and then by linear superposition, you can have a state like alpha up plus beta down. This is a quantum bit, and here you have classical bit kind of thing. But when you do measurement in a quantum state, we know that the quantum state will tend to collapse. So you will either find up or down. So you will end up again in classical information scenario. So when you think of a two quantum bit, what happens? So we know that two classical bits can remain in any one of these four logical states like 0, 0, 0, 1, 1, 0, 1. So if you think of two quantum bits like two spin, they can also remain in 0, 0, 0, 1, 1, 0, 1, 1, which means you can have up, 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 down, down, up, and down, down. But then by superposition principle, you can have a scenario where your two quantum bits can remain simultaneously in all four logical states. So that is the difference you see from here to here. And if you think of n quantum bit, then the possibility really grows exponentially. So in classical computer, your n bit can remain in any one of these 2 to the power n possible logical state. Means given this n classical bit, at a given time, you can find all the classical bit either 0, 0, 0, all 0, or maybe all 1, or maybe 0, 0, 0, some of them are 0, some of them are 1, and in that kind of scenario. But if you think of a quantum bit, think of n quantum bits, in short, which you call n qubits, you can have 2 to the power n possible state. But what is remarkable here is you'll find a situation where this n qubit can remain in all those exponentially large number of logical states. So that is the beauty of quantum theory, which allows you to grow your possible logical states and having its access to exponentially large number of logical states. So for n equal to 300, this number goes like 10 to the power 90, which is more than the number of atoms in the known universe. You see how vast this number of logical states is actually. So quantum computer take the advantage of this exponentially large number of logical states, which leads to this basic parallelism. So if you ask the question, what can you do with quantum computer? There are many things you can do, but there are limitations, and still we don't know many things how to really design universal quantum computer. But there are over the last 30 years there have been tremendous progress. So technological revolution from quantum computers may allow to resolve or solve problems that are currently too complex for classical supercomputers. So in early days, there are a few algorithms that were discovered starting from Source, Grover, and Doge algorithm. So all of you, might have seen that there is this famous Source prime factorization algorithm, which can be used for factorization problem. And there was this database search. So classically, if you have n entries in a database, classical computer takes the order of n steps, but quantum computer can do in square root of n steps. That is square root of improvement you get by using this quantum computer. And there was this Doge algorithm. Actually, this is the first algorithm that was discovered and tried to essentially this was designed to show that quantum computers are really powerful. So this was not something you can use in practice, but kind of artificial problem. But it was designed, as I said, to show the true power of quantum computers. What they showed in that paper was if you demand some condition on some nature of some function, then classical computer takes exponential number of steps, whereas quantum computer can take only, you can do the same thing just in one step. So you see exponential number of reduction in the number of query, deciding that nature of the function. So that is kind of task you can achieve with quantum computer. And as you might have seen over the last 5 years or so, building a quantum computer is the race of 21st century. This is a very difficult and ambitious challenge. And once you build it, this has a potential to revolutionize future computers that can do impossible calculations with a plethora of useful applications in healthcare, defense, finance, even chemistry and material design, or maybe software debugging, aerospace, and even in transport. The speed and power of a quantum computer lie in the fact that quantum systems can remain in multiple quantum states that occur only at quantum level. And we need to bring quantum computing to commercial reality, and we need an extraordinary team to put the effort. That is why there is a lot of demand, a lot of funding, a lot of investment happening in this area. And some of you might have already seen that in 2016, IBM initiated to build a quantum computer which is commercially available. Like they started with 5-qubit computer, and in May 2017, this IBM Q was announced. This is a prototype commercial processor with 17 qubit, and that was significant improvement over the earlier one. And you can do most powerful, computing with this device at that time. Last year in September 2020, IBM announced 65 qubit, and they have planned that by 2021 they will try to establish like 127 number of qubit. By 2022, maybe about 433, and by 2023 they may go about more than 1,000 qubits. And once a company develops this kind of device, they can allow for developers, for programmers, and even for researchers to implement quantum algorithms. And more than 30 companies have already started investing hugely in quantum computing and quantum information. Still, there are more, but notable companies may be about more than 30 or 40. And what you hear over the last 2-3 years is some of these companies are trying to achieve so-called quantum supremacy and quantum advantage. So these are keywords you hear in newspaper and so on. So let me try to tell what exactly this means. So if your quantum computer can solve a problem that no classical computer can solve in any feasible amount of time, irrespective of the usefulness of the problem, then you will say that yes, your computer is able to achieve supremacy. And there is this similar notion that is called quantum advantage. That means if you can demonstrate that the quantum computer can solve a problem much faster compared to classical computer, then you will say it has quantum advantage. And in 2019, Google has claimed that they had built a quantum processor with 54 number of qubit, and it could check the random number generation in 200 seconds, whereas the best supercomputer at that time would take about 10,000 years. So you see the power of this quantum computer. In same year, 2020 December, Chinese team they claim that they designed another processor which is 10 billion times faster than Google's processor, and it also took 200 seconds, whereas world's fastest supercomputer might take approximately 2.5 billion years to carry out the same calculation. So this means these two quantum computing device or quantum computing processor, they show really quantum supremacy. So there is this notion about quantum entanglement. Whenever you think of quantum computing or quantum communication or quantum technology, you have to deal with quantum entanglement. So what is this entanglement is all about? So this kind of feature or notion comes into play when we have more than one particle, like 2 or 3 or n number of particles. So what happens is you have multiple number of particles. The quantum system can be found in a strange kind of state, which is kind of intertwined or kind of end-to-end state, which we call entangled state. So once you have this entangled state, individual quantum systems, they are not independent. So if you want to, I'm not going to rigorous definition. But if you want to define, what these entangled states are actually, it means that we know that in quantum mechanics, the most important thing is wave function. That means you can associate a wave function to a quantum system, but if you have entangled state of two particles, then you can associate a wave function for the joint system, but you cannot associate a wave function for individual system. That is one of the simplest way to imagine what these states are. That's what I mean. They are not independent, and you cannot associate a definite quantum state to each of the particles. And they are linked in a strongest possible way, even if they are far apart. And this is the kind of weirdest feature that you see in quantum world, and that allows you to do imaging tasks which are otherwise impossible. And I will try to highlight some of them during my talk. And this quantum entanglement involves entwining or interconnecting two or more particles without physical contact. That means if you are able to create an entangled state in your lab, and you take one particle to say Delhi and one particle to to New York, once they are entangled, even if they are far apart, without any physical contact, they will still be remaining in an entangled state. And that provides an invisible link between two or more particles, which you can use for quantum communication. And this notion was actually introduced by Schrödinger, whom we all know in quantum mechanics, same person who discovered Schrödinger equation in 1935. And in same year, Einstein, Podolsky, and Rosen, they came up with an argument using this entangled state, and they tried to show that there are some features about entangled state which try to which are leading to some kind of uncomfortable situation with the predictions of quantum theory. So they thought that maybe quantum theory is not a complete theory, because Einstein was kind of person who was never satisfied with the development of quantum theory, with its probabilistic prediction and so on. So he thought of a theory where everything is deterministic, everything is having a realistic feature and so on. So what he came up with this paper in 1935, he tried to argue that quantum theory is kind of theory which is not a complete theory. Maybe there is more deeper theory than quantum theory, and in some limiting case, quantum theory will be kind of special case of that larger theory. But over the years, it was realized that these entangled states are having much more use than what Einstein thought about. Even though they have this kind of spooky action, but now we can use this spooky action to exploit quantum computation and quantum communication. I'm not going again in detail of this CPR paper, but I thought I will just tell a little bit about the history of this paper. Okay, so coming to this quantum bit and its nature and how they differ from classical information, let me tell you a few things. That quantum bits are some kind of, they maintain their privacy. They don't reveal what is there inside, unlike classical information. Because classical information, when you manipulate in your laptop or in your desktop or even in your mobile, anyone can copy the information, anyone can delete, anyone can do whatever they want. In principle, there may be password, there may be some secret key and so on, but in principle, nature does not prohibit you to copy the information. But when you think of a quantum information stored in qubit, they maintain some kind of privacy. That privacy actually comes from the fundamental features of quantum theory. Not that you design or you manipulate or you put a password and things like that. No, not that. It is actually coming from the fundamental laws of quantum theory, or fundamental principles of quantum theory. So it is more to do with how nature manipulates information at quantum level. It is not you or not me, but it is, it is given by nature. So this first kind of thing that you see is something called no cloning theorem. It was discovered in 1982 that proved that quantum information cannot be copied. That means if you store information in the quantum bit, only you can make a copy. Nobody else in the world, nobody else in the universe can make a copy of that information. So you see, so-called the issue of piracy will completely disappear once you make quantum devices, quantum computers, and so on. So only the person who is using, who has stored the information, he or she can make a copy. Nobody else can make a copy of the information. And then in 2000, we discovered something called no deletion theorem that tells you that quantum information cannot be deleted. That means if the person who is created, who has stored the information, if he has 2 copies of the information in a quantum system or quantum computer, nobody else can delete one of the copy and keep the other copy intact. So this is kind of limitation, kind of restriction that is coming due to the nature of quantum theory. And there is another limitation called no flipping. What happens is with classical information, we know that you can design NOT gate, which is one of the useful gate in classical computing. But if you want to design same NOT gate, which will take some state psi to its orthogonal state, cannot make that possible. That is called no flipping. And in 2007, we tried to prove something called no heading theorem. It tells you the following: that suppose you have stored some information in quantum state and something happens to your system, and at the end of the day, your information is lost. That means you lose information. Then this theorem is trying to prove that actually information is not lost. It simply moves to another subsystem, and from that subsystem, actually you can recover the information. This is called actually conservation of quantum information. So this was proved theoretically in 2007. In 2011, it was proved. This theorem was actually proved experimentally by Professor Kumar, who is also present here, and one of his students, Jarana Samal. Unfortunately, she is no more in a tragic incident. We lost, and she is no more now. But one of the bright students, along with Professor Kumar, they carried out the experiment in NMR, and they actually tested that yes, indeed it is so. So what they did was actually they took one of the spin, with NMR setup, and then they tried to apply some operation, and at the end, the information is actually lost, and then they could recover the information from one of the qubit, which is acting the ancillary system or environmental system. From there, one can recover the information. And this is one of the beautiful experiments we actually tested this prediction. And very recently, we tried to prove something called no masking theorem, which tells you the following: that typically, when you think of a quantum computer or quantum device, we store information in physical system. Okay, that's what I started in my first slide. But in this paper, what we do is we ask the question that can you store information not in the physical body, but in the correlation between the physical body, in some kind of invisible form. Okay, that means you take some information, you encode it to a larger system, so that each of the individual system, they have no information, but if you have the joint system, you will be able to recover the information. Is it possible? The answer is no, this is not possible. But if you go to more than 2, that is 3, 4, or maybe multiple number of particles, it may be possible. So what is the implication of this? The implication is the following: that if you want to store information in a larger set of states, then individual particles will not contain any information. That means you can store information secretly in a network where it is stored in a collection of systems, but individually they will not be able to access the information. But when they come together, when they collaborate, even you can extract the information. It will have application in that kind of scenario. And these results have deep implication in quantum information and quantum computing and quantum communication. So let me come to the quantum information. The whole area of research over the last 30 years. So what is the big picture here? This is one of the vast growing field. So one of the main goals in quantum information science is how well you can store, process, and transfer information using principles of quantum theory, quantum mechanics. This is the main goal in this area. And what you do is you try to exploit features like superposition, entanglement, and non-locality. And using these features, you can do practical tasks, like you can do some application, you can do some imaging tasks which are impossible otherwise in classical scenario. So when you think of quantum communication, typically what you have in mind is you have two person, Alice and Bob, and Alice and Bob, they share a quantum channel. And this is essentially your entanglement that I talked about a little before. And Alice is allowed to do whatever she can do remaining within quantum theory. That means what is allowed by quantum theory, that kind of things she can do in her lab. She can do unitary process, she can do measurements, she can do, generalized measurement and so on. And then depending on her action, she can send the classical outcome through classical channel. Bob is also allowed to do whatever is possible remaining within quantum theory. And then they can do back and forth and so on. And at the end, they will be able to achieve, some quantum communication task. Okay. So over last 25 years or so, several things have been discovered, starting from quantum teleportation to super dense coding, to remote state preparation, to quantum secret sharing, quantum cryptography, quantum internet, and many more things actually. But I have tried to highlight a few things. Let me tell you what this teleportation is all about. If you're not familiar, some of you already know. So if you have seen the movie The Fly or Star Trek serial in Hollywood, you have seen that there is a device and a person enters the device, and he or she presses a button and he, appears in another planet, without physically traveling the intermediate distance. That is kind of teleportation. So dictionary meaning of teleportation is destroying the object at one location and recreating the same object at a distant location. That is the meaning of teleportation. Okay. So this kind of bizarre task is actually possible in quantum theory, or quantum world. So this is called teleportation of quantum bit. So you have a person Alice and there is another person Bob, and they own a company, which is a teleportation company, and then somebody comes and gives his quantum state and asks Alice to teleport the quantum state. And before 1993, it was thought that maybe it is not possible to teleport a quantum object. Why it was thought like that? Let me tell you, because that will give you better insight to what is really going on. Because the person who is coming and giving a quantum state to Alice, she is giving only one quantum state, a single quantum. Okay. So a possible scenario for teleportation would be that Alice should do a measurement on this input and extract the information and send the information over some classical channel, and Bob will have some raw material, and Bob will, reconstruct the quantum state from this classical information, and then at the end, teleportation may be complete. This is one possible scenario. And I'm not saying this is the only scenario, but one of the possible scenarios. But there is a catch now. The person who is coming and giving the state to Alice, he or she is giving only one copy of the quantum state. And we know that in quantum mechanics, given a single quantum, you cannot read the information, because once you start reading it, once you start doing measurement, the quantum state will collapse. So you will lose the quantum state. There is no way to know the information what is there in the quantum state. That means Alice will not be able to do what I just said before. Okay. Then she may think, okay, let me try to make several copy, and then from there I can try to determine the quantum state, and then I will transfer the information to Bob, and Bob will be able to reconstruct. But again, by no cloning theorem, this is not possible. Alice cannot make a copy of quantum state. Forget about making n copy, but she cannot even make a 2 copy. Okay, that means this strategy is also going to fail. But very miraculously, very surprisingly, in 1993, Charles Bennett and many other people, they discovered that if you have this quantum channel shared between Alice and Bob, which is your entangled state, then there is a way to teleport the quantum state even without knowing what is there in this quantum state side. So what Alice will do, again, there are technical detail I'm not going to tell. Somebody else may cover this topic, but this kind of overview, so I'm not going to tell the mathematical steps. But essentially, Alice will do some kind of joint measurement on the input and this entangled one half of the entangled pair, and send the measurement outcome because you see this is a single qubit, this is also qubit. So the Hilbert space of this qubit is 2 times 2 is 4. So number of measurements you can do and get the outcome is only 4. So that log base 2 times 4 is 2 classical bits. That 2 classical bits you will send to Bob, and Bob will do something on this half of the entangled pair. And at the end, this half of the pair will get transformed exactly to one of the replica of this psi. And in the process, this psi which was present here, that will get destroyed. Otherwise, you will violate the non-cloning theorem, which is not possible. So this had to get destroyed, and then the state will appear here. So you see what is going on. The really miraculous way of sending quantum state without physically sending from Alice to Bob, without knowing what is there inside, without sending the full information. You are sending only 2 classical bits, whereas to describe the quantum state, you need actually infinite number of bits. So this is a really a miraculous way or magical way to send quantum state from Alice to Bob. Okay, that is why this is one of the most beautiful, most famous quantum communication protocol in quantum information. So first experiment came in 1997, immediately, just 4 years after this theoretical proposal. This was done by Jelling group in Vienna, in Innsbruck, in Austria. And the distance was not much, about few 1 meter distance, but later on people try to teleport from light to matter from two different objects and to over long distance. And they try to do also so that eavesdropper cannot have access to the information, and they can be made unconditional secure and so on. So this is the team who did this teleportation from between two different objects. And then Geneva team, they try to teleport over about 1.2 miles, and then slowly they also done over long distance later on, but I'm not listed here. And then in 2016, this Pan group in China, they developed teleportation over optical channel using free space communication over about 16 kilometers. And this Japanese group, they teleported over 100 kilometers in 2015. And as you might have seen, a few years back, the Chinese group, they teleported single photon from ground observatory to low Earth orbit satellite using uplink channel over a distance about 1,400 kilometers. This is the latest record they have achieved. And they could also quantify how good that is. That is, they could teleport the quantum state within fidelity of 0.8. Fidelity is a measure where it tells you how good it is. If it is 1, it is perfect. If it is less than 1, it is not perfect, but it is, if it is close to 1, you are satisfied, kind of thing. There is also a limit, if it is less than 2/3, it is not good, because that is classical limit. But if you can achieve more than 2/3 fidelity, you can say it is, you can claim that is quantum teleportation is kind of truly quantum. But again, that is detail. I'm not going to tell all those details now. So there is another protocol called super dense coding, which shows that quantum entanglement not only useful for quantum communication, but also useful for classical communication. So that means the following: you can send single bit, and you can achieve 2 classical bits. Typically, this is not possible, because we know that if you single quantum bit, you can convey only 1 bit. But if you use entanglement, you can double the capacity. Okay, that is why this is called super dense coding. And the scenario looks like this: you have 2 person, Alice and Bob, and Alice receives 2 bit, and she encodes, and then sends a particle, just 1 qubit, and Bob has already another qubit beforehand, and he will do decoding, and he or she can get the 2 classical bit. And remote state preparation is another idea, which is the following: that Alice wants to prepare a quantum state Bob place without sending it physically. So what is the difference between teleportation? Here, in remote state preparation, the idea is Alice knows the quantum state, whereas in teleportation, the state is not known to Alice. So even if Alice knows, if she want to convey the information, she had to convey infinite number of classical bits. But using entanglement, we have shown that you can send just one classical bit and Alice can prepare the quantum state without physically sending, to Bob. So that was done in actually 1999, but it appeared in 2000. And this is also tested by many groups using photons and other setups also. And here is the scheme that you can visualize. So Alice and Bob, they're separated, and Alice has a quantum state in her mind, and she can do some measurement on this quantum state and send just one classical bit, and then at the end Bob will do something and get the state that Alice wanted to prepare. Okay, this is called RSP of a quantum bit. And there is also secret sharing in classical information. So Alice and Bob, they want to have joint account. Neither of them can have access to the account alone, but together they can withdraw some money, for example. So that requires some password, secret password. So neither Alice and nor Bob, they have the password, but Alice has a string of random number and Bob has a bitwise XOR of the key, and Alice has a bit string. That is, a key is equally this. But what Alice and Bob have, they have is this string and this string. Okay, so if you look at Alice's string and Bob's string, that doesn't have this, this key. Okay, but if they come together, they can do bitwise XOR addition modulo 2, and then they get back the key. Okay, that means they can withdraw some money. And this kind of scenario has been generalized to quantum states, and that is the whole idea of quantum secret sharing, and that allows you to share a secret among 3 or more people, so that any two of them can reconstitute, but any single person cannot do that. So next, coming to cryptography, is again quite old idea in information, classical information. This is the art of encrypting and decrypting message in codes in order to ensure their confidentiality and authenticity. Okay. The fundamental task of cryptography is to allow two users to have secret communication, which is unintelligible to third party. That is the main idea. So essentially, you have plain text, then you encrypt using some key, and you send ciphertext to the channel, and the person who will receive, he or she will decrypt and will get the plain text. And one of the very famous example is your cipher and one-time pad. So in quantum cryptography, you can also imagine a similar scenario, which was discovered by Charlie Bennett and Gilles Brossard in 1984. So you have 2 persons, Alice and Bob, and Alice has some quantum state in which she encodes information, and then he sent the quantum state to the quantum channel, and then they can also discuss the outcome of this measurement with classical channel, and Bob will do also some checking, and at the end they will establish some secret key. Okay, so there is another idea called quantum internet, and that was proposed by Jeff Kimball in 2008. So what you do here is you store information, that is you encode and process and store in local quantum nodes, and you can connect nodes by quantum channels. When I say quantum channel, it could be entanglement channel, or you can use teleportation, or you can use remote state preparation, and you can transport qubit from one side to another side. And you can distribute entanglement over entire network. That will lead to quantum internet. So in future, there is possibility that you can download entanglement, you can use it for quantum computation or maybe for quantum communication and so on. And you can also return it back to the quantum internet network, So that is the possibility. So typically, will look like this. So long distance communication is possible. You have this local quantum node, and then you can connect through some quantum channel. So quantum technology is quite promising. This has far-reaching innovations based on fundamental laws of nature, and quantum technology will make devices smaller, faster, and much more powerful than the present-day devices. And this could comprise quantum computers, quantum software, quantum information system, quantum communication scheme like teleportation, RSP, and quantum internet. And there's other applications like design of precision atomic clock and quantum algorithms for tackling hard problems and for space quantum key distribution. And it will change nearly every aspect of future life. There is no doubt about that. So quantum information or quantum technology is truly an interdisciplinary science because you need experts from quantum theory, you need from computer science, from engineering, from information theory, from communication and cryptography, and many more areas. So you see, that is the main reason why over the last 20 years, there have been tremendous curiosity and interest from researchers from various disciplines, various areas of science and engineering. Okay, so I am almost close to my talk. So let me try to summarize what I said. So quantum mechanics allows you to do something completely different than what you have thought in classical world. That allows you to, a new way of storing and processing information. And quantum information is fundamentally different than classical information because it exploits the principle of linear superposition and quantum entanglement, and it gives the power to quantum computer, which you don't see the classical computer. And the quantum computer can perform certain computational tasks much more faster than classical computer, and that is the main reason that there is a global race to build quantum computer. So it's not that quantum computer can, they can solve everything faster, but you have to figure out what they can do, So, and I tried to highlight also quantum bit how they maintain the privacy. They cannot be copied, they cannot be deleted, you cannot flip, and you cannot mask it. So all these limitations tell you that information is secure at a more fundamental level. Okay, and quantum information allows a new way of communication which are impossible in classical world. So I try to give flavor of this communication protocol, starting from teleportation to superdense coding to remote state preparation and secret sharing, quantum cryptography, and quantum internet. And there are many more you can see in the literature. And quantum communication can allow a completely secure way of transferring information. And quantum teleportation is an important protocol that will make one-day quantum communication over long distance possible. And quantum entanglement is actually a key feature in this, and that provides invisible link or invisible wiring between different locations, nodes in quantum communication channel. So one of the biggest challenges is to produce entanglement over long distance. And next revolution will be quantum computing, quantum communication, and quantum information technology. There is no, without any hesitation, you can safely say that you're going to see a true revolution in next couple of years. Okay, so today's basic science is tomorrow's technology. So we should, encourage both. Yes. So stay motivated and witness the quantum revolution. Okay, so thank you for your attention.
Yeah. Thank you, sir. It's a very inciting and very good for information and introduction to the quantum computing given by Professor A.K. who is working since long in this area. And so that's a very fine lecture given by Professor A.K. And it is anticipated that in the next 10 to 15 years, we have in our hand like quantum computers. From so many literatures, we have found this. So no doubt that this quantum computing will change the whole scenario of the scientific world in future. So thank you very much, sir, for your this presence and to give a very valuable and sufficient lecture to our participants. Thanks a lot, sir.
Thank you.
Thanks. So one announcement for participants that as you know that for AICT rules for this FDP program, a test shall be conducted maybe online at the end of this program, that is on 8th of October. Okay, so first this is very important. Second is that the certificate shall be issued to those participants who are registered and attend the program with minimum 80% attendance and score minimum 60% marks in the test. So this is given by ICT for our participants. So I request all participants to attend this FDP or the whole session or like 3 lectures in one day. And that would be really very beneficial to everybody. Okay, so next lecture that would start from 11:30. So you will present here in the same session at 11:20. I request everybody to present at 11:20. Okay, so again we will meet at 11:20 a.m. Thank you.